We begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Just pray that you guide our work today and prepare our hearts for the break, which is about to start, Lord. Amen. Soon. So for you guys, tomorrow. We will not meet tomorrow. You guys can go play, frolic about, whatever it is you do. We should still, so if things go as I planned today, I will have all of the required material more or less at least somewhat discussed. And then the week when we come back, I don't think on the next test I have anything beyond, do I have anything beyond convergence, divergence? I don't remember. I don't think so. So the next test is on convergence, divergence, and improper integration, L'Hopital's rule. The test is not next Tuesday. It is the 17th?
Oh.
What?
I could have sworn it was like Thursday.
Is it Thursday? That's when the...
Yeah.
Oh. You're going to go back the most you're going to do is talk, bro.
Yeah.
Why you bro, you're going to be, wait, please tell me you started. Why y'all did you start it?
All right, so definition. So anyway, what I'm trying to say is I'm not taking many homework questions today because I want to make sure I get all the, I want to make sure I tell you guys all of the main theorems, and then if we have time left at the end of class, I'll take homework questions. I'll be here tomorrow after the test, the class I teach earlier, and I can answer your, if you had a couple homework questions, I can answer them for you individually then if you want, or office hours, of course. Anyway, let me just try to get through it, and then if we still have time for questions at the end, I'll take them. So here it is, the series sum over a sub n converges absolutely if the sum of the absolute value of a sub n rather, converges. So absolute convergence, or this is also known as absolute convergence, of the series. Now, so you're like, well, is this the same idea? I mean, are there series which are not absolutely convergent, right? So here's a good example. Worthless. Too much trash. So this one we talked about we proved this converges last time, right? Sum n equals 1 to infinity, minus 1 to the n plus 1 over n. This is the alternating harmonic series, right? This was 1 minus a half plus a third plus dot, 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 dot. I mentioned to you guys that this actually converges to the natural log of 2. We haven't proved that yet. So this in fact converges. The reason this converges by the alternating series test, which we went through the details of last time. Okay, how about this then? What is the absolute value of this series? And by that I mean, what's the term by term absolute value of the series? What happens if you take the absolute value of the alternating harmonic series? What do you get? We just get the plain old harmonic series, right? So this, of course, is p equals 1 diverges, right? So this is an example of what? This is an example, so we call this S. So S converges, but does not converge absolutely. So this S is not an absolutely convergent. Yeah.
What's the difference between that and conditional convergence?
So definition, such a series is called conditionally convergent. It's okay. It's like it's like this is a magic act, and you're my plant in the audience, so I'll allow it. But yeah, a series is said to be conditionally convergent if it's convergent, but not absolutely convergent. Yeah.
When you took the absolute value of that term, is it supposed to be n or n plus 1 and y?
Oh, it should be n plus 1. And the larger point is minus 1 to the n plus 1, right? It's equal to plus or minus 1, right? So when we take the absolute value of minus 1 to the n plus 1, I mean, it's just 1, right? But yeah, that should have been n plus 1. That was just a typo. Thanks. There's a theorem which would be pretty much useless for example 1, but the theorem is this, which is that absolute convergence implies convergence. In other words, if I have the sum, well, let me skip the lower thing. The sum of the absolute value of a sub n converges. In other words, it's a summable series. Then that implies that this guy converges. So here's the proof of that. So assume that the series absolute value of a sub n converges, right? Then how is a sub n related to the absolute value of a sub n? Oh, I'm going to get into trouble. There's something sneakier that's required here. So the book has us looking at a different inequality. He points out 0, and let's see if you guys agree with this. 0 is less than or equal to a sub n plus the absolute value of a sub n. Does that make sense? So if a sub n is positive, a sub n plus a absolute value is just twice a sub n, right? If a sub n is negative, then it's just 0, right? But either way, it's not negative. And then this is less than or equal to what? How about 2 times the absolute value of a sub n? Right? So let's see here. What can we do with that? So this implies that the sum of a sub n plus the absolute value of a sub n converges by direct comparison test with 2 times the sum of a sub n, right? We're given that the sum of the absolute value of a sub n converges, consequently, this smaller series must also converge, right? Because it's important that this is a series with positive terms, right? Well, non-negative terms, more to the point. Okay? But then what? A sub n, what's a sub n equal to? A sub n is equal to, now this is kind of sneaky, but it's equal to a sub n plus the absolute value of a sub n, right? Minus the absolute value of a sub n. And so you might notice that the series a sub n then is equal to the series an plus the absolute value of an minus the absolute value of an, which is equal to the series, and this step I'm making assumes what? I can break a series of a sum into the sum of the series provided, or difference in this case of series, provided that the series which you get to both separately exist, right? These both exist, both converge, because we just proved that by direct comparison this converges. We're assuming that the absolute value series converges, right? So I have this converges, that converges, so I can apply the one of our series rules, which I should probably prove. I haven't done it yet, but the one I'm using, of course, is if the sum over, let's say, an and the sum over bn exist, then we have the following. The sum of an plus bn is equal to the sum an plus the sum of bn, and also same song and dance with a minus there. But that assumes that the terms an and bn both give us separately convergent series. And you notice, so, well, it's unfortunate. I guess I should use different letters. Let me use a capital A and capital B over here so you can see the difference. Sorry about that, guys. If I use capital A and capital B, then I can make a correspondence between this theorem, which I have not yet proved, but we could prove. It wouldn't be hard. So I'm thinking of this as being the an. I'm thinking of this as being the bn in my sum and difference of series theorem. So anyway, this shows that the series built with term an converges automatically if we know that the corresponding absolute value series converges. Does that make sense? Yes, no, maybe so? Let me talk about the proof of this before I forget. It is something we should actually do. So suppose that the sum, let's say n equals 1 to infinity, an, and the sum n equals 1 to infinity bn converge, right? Then we can define the eighth partial sum for a words. So the partial sum for a, let's say s upper an would be the sum, j equals 1 to n of a sub j, right? And we can define the nth partial sum for b, let's say s upper b sub n sum j equals 1 to n of b sub j, right? And consider the series that's the sum of, let's say, a constant times a sub n plus b sub n. So this is n equals 1 to infinity. Consider this series. What's the nth partial sum of that series? What's the nth partial sum for this one? Let's call it S sub n, yeah? It's the sum j equals 1 to n of what? Of c a sub j plus b sub j. Now, there's a property of finite sums that we could prove, but I won't, but it's fairly easy to prove. And the property of finite sum says that you can pull a constant out and you can break it into the sum of terms like this. Now, the way to prove that would be with induction on the recursive definition of the sum. And I can show you that if you're interested. But this is a property of finite sums. You can break up across addition and you can pull constant out. Right? Here's a sketch of a proof. Not quite a proof, but I'll show you why that's true. Not quite a proof, but what is that? You know, Sn, it's equal to what? It's like CA1 plus B1, right? Plus CA2 plus B2 plus dot plus CAN plus BN, right? If you rearrange terms here, you can factor the C out, and you got A1 plus A2 plus AN plus collect all my B's together, like that, right? But that's exactly C times the sum j equals 1 to n of A sub j plus the sum j equals 1 to n of B sub j. Which is what I wrote down there, but I just thought maybe it'd be good to give you guys some explanation for why that's true. It's nothing mystical, it's just algebra. Finite algebra. N is finite. And what is this? Well, this is C times what I called the nth partial sum for A, right? And this is just the nth partial sum for B, right? What happens as n goes to infinity? So this is basically how we prove the sum rule for series. Given that these two series exist and converge, I mean, given that these two series sum to whatever they sum to, then it follows that let me write down the conclusion again here. The conclusion is just that we can break n equals 1 to infinity of CAN plus BN. We can break that up into the sum n equals 1 to infinity, pull out the constant AN plus the sum n equals 1 to infinity BN. Like that. If I'd been smarter, I would have put the constant on the B term, and then we could have choose constant minus 1 to get the minus. Right. If you like to, though, you can take B to be 0, then you can see that you can pull a constant out of a series, right? And if you look at this proof and you study what we're saying, it's also clear that if you have a divergent series and you multiply it by a number, it's still divergent, right? If you have a convergent series, you multiply it by a number, it's still convergent. We use these in examples, right? Any questions about this? Yep. Oh, I said that wasn't the theorem that I stated. I just decided about right here to let C be a real number because I thought, as long as I'm after this, I might as well prove it for a constant because it's the same calculation. Just put the constant here and you can pull it out and then we get this result. This is basically the theorem I'm trying to sketch the proof of. which is that the sum of the series is the series of the sum, provided that these both exist. And also, we can pull out scalar multiples. But it's, with the right interpretation, you can always pull out a multiple, right? If I understand the interpretation correctly. I mean, what I mean by that is if we agree that a constant times infinity is still infinity, then maybe this equation still even makes sense when the series is divergent. Because like 3 times the divergent series is still divergent. But if it's convergent, then if the series converges to 2, right, and I multiply it by 3, then this one converges to 6. I'm not saying anything terribly shocking or anything here. All right. Anyway, I wanted to talk about that because technically speaking, I actually had to use that theorem to make this step right here, right? Like, because I'm using that these two series, the difference of these two series gives me that. And because both of these exist, it follows that exists. And so, yeah. Admittedly, it's something I should have proved days ago, but I have tried to spend the preponderance of our time working problems in here as opposed to proving things, so there you go. But at some point or another, it eventually wears on me that I haven't proved anything, and I feel obliged to prove things, and then, well, here we are. Yep.
I had a question about the series scoping. So, like, if an alternating series, like, is just like alternating and stuff, right? I thought like -1 to an n plus 1 on that. Like, how does that converge down to?
I haven't explained that. Yeah, we don't know that yet. I mean, I told you guys it's true, but I mean, the fact that it converges is by the alternating series test. The fact that its sum is actually log of 2 is something we don't really know how to explain yet. Yeah. Here's one. So, something like -1 to the n plus 1 over n squared, n equals 1 to infinity, there's different ways you could attack this problem. The one way is to say, okay, well, note, let's say this is S. So note that, observe that the sum, we will explain that, Darius, but it will be, after the test. So no need to sweat it for now. We do not have the technology to answer that question yet. What's the absolute value of this series, term-by-term absolute value of this series? I mean, absolute value kills -1 to the n plus 1, right? And so the corresponding absolute value series is just what? Right, so this converges by what? Right, p equals 2 series test. AKA, you could just say, hey, this is p equals 2 series, it converges. Thus, S is absolutely convergent, hence S converges. Because absolute convergence implies convergence.
What that would converge to power squared over 6?
I don't know what. No, well, yeah. Again, it's same flavor. I will write this down, but this is actually worse. Like log 2, I'll explain eventually. This I might never explain in here. That's actually pretty tough to derive, but yeah, it's true. Yes, sir.
Do we not need to prove that the original series converges?
We did. By showing that it's absolutely convergent, that proves it's convergent because we have the absolute convergence theorem. Yes? Oh, just stretching. Okay. Example 2. Example 2. How about this? The sum n equals 1 to infinity of, I don't know, the cosine of pi n over 1 plus n squared. What's the cosine of pi n? Yeah, cosine of pi n is actually equal to minus 1 to the n. That's just a stupid way of writing minus 1 to the n. Check it out. N equals 0. Cosine of 0 is 1. Cosine of pi, minus 1. N equals 2. Cosine of 2 pi, 1. Cosine of 3 pi, minus 1. Cosine of 4 pi, 1. Cosine of 5 pi, minus 1. And back and forth and back. It's the same function. So, yeah. So, we can consider the sum n equals 1 to infinity of the absolute value of an is equal to what? So I'm going to call this thing an, okay? So this is just what? 1 over 1 plus n squared, right? Yep.
Graphically, doesn't that just look like you just took away like the bottom part, so wouldn't it still like kind of more or less like why wouldn't that ever? It's just like it's like the humps.
Well, the I mean, if the absolute value of the series term by term diverges, that doesn't really help me. So, but if it converges, and my sense here is that it will, because this is really kind of almost the same as the last example. I just added 1 to the denominator in some regard. You know? So I want to say that this is going to absolutely converge, and consequently I can argue that it's convergent by the absolute convergence theorem. That's my thought process. How would you, what is it?
Why doesn't it look like that graphically?
Why doesn't it look like that? Well,
What's the absolute value if it doesn't like go down like this?
what is it?
Or that's a sign.
I mean, what this thing looks like is, so this is, I mean, I guess I can try to graph it. 1 over 1 plus n squared, if I continuously extend it, looks something like this. All right? Minus 1 over 1 plus n squared looks something like this, roughly, very roughly speaking. So I'm looking at y equals minus 1 over x squared plus 1. And upstairs, we've got y equals 1 over x squared plus 1. And then this thing is alternating between those, like n equals 1. It's like here. Oh, I'm sorry. N equals 1, it's like here. N equals 2, it's here. 3, 4, 5, 6, 7, 8, you know, bouncing back and forth between these two envelopes with plus, minus, plus, minus, plus, minus, plus, minus. But it's always between these two guys. And of course, they both go to 0, which is not a proof that the series converges, but it's hope. I mean, that's just kind of evidence towards a sub n going to 0 as n goes to infinity, you know? Which I suppose you could prove with the squeeze theorem or something like that. I mean, for a sub n, we had the theorem that if the limit of the absolute value of a sub n is equal to 0 as n goes to infinity, that implies that the limit as n goes to infinity of a sub n is equal to 0. And in fact, it goes both ways in this case. But that's a sequence. We're talking about series. Okay, so you guys tell me. I mean, I can think of 3 ways to do this. 3 ways. I could do integral test. Because, hey, I can integrate 1 over 1 plus x squared, right? Yeah. I think I could do direct comparison test. Because 1 over 1 plus n squared is what? It's positive, right? And it's less than or equal to 1 over n squared, yeah? So I could do direct comparison to p equals 2. Or, of course, the other thing I could do would be a limit comparison test to p equals 2. Pick your poison. whatever you do, we all agree that the series 1 over n squared plus 1 converges. I won't belabor the details at the moment, but it converges, therefore S converges absolutely, which implies that S converges by the absolute convergence test theorem that I have on the middle board. So, I mean, generically speaking, this absolute convergence test is super nice for getting rid of some pesky plus or minus thing you don't want to deal with, you know. But of course, you can also use the alternating series test for a lot of these examples. Let me just share with you guys another fun thing from this section. This'll. I have to write this down because I can never remember how to do this myself. I have to cheat here, if you don't mind. So here's the alternating harmonic series, right? So you've got the sum n equals 1 to infinity, right? Minus 1 to the n plus 1 over n. And so this is 1 minus a half plus a third minus a fourth and plus dot 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 dot. As he says, that works out to log 2. So he says, consider the rearrangement below. So he's going to start out with, instead of like that, he's got 1 minus a half minus a fourth, right? Plus a third minus a sixth. Let's see here what's going on. Minus an eighth plus a fifth minus a tenth minus a 12th plus a 7th minus 1/14th minus dot 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 dot. He says this is equal to, if you look at it, that's equal to 1 minus 1/2, right? Minus 1/4 plus what? Plus 1/3 minus 1/6 minus 1/8 plus 1/5 minus 1/10 minus 1/12 plus 1/7 minus 1/14. All right. Which is what? This is 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12 plus 1/14 dot dot dot. And then we can factor out a half, right? 1 minus 1/2 plus 1/3 minus 1/4 plus dot dot dot, right? Let's see here if we can understand what just happened. So this original thing, this expression right here underlined in red, can you see that these have the same terms in it as these? I mean, I haven't written quite enough to see it yet, right? But what's past here? Plus a fifth, minus a sixth. Wait a minute, how did that happen? Minus a, oh yeah. Right. Plus a seventh, minus an eighth, plus a ninth, minus a 10th, plus 11th, minus a 12th, plus a 13th, minus a 14th. And as I told you, and I haven't proved, but it works out to log 2. This one does. So if you look at these, all these terms, right? The same terms are present down here, right? What did we do? We just rearranged it, right? I moved the third. We juxtaposed the 4 and the 3, right? What else do we do? We moved the 5 and the 6 around, right? You see what I did? Like if you look at these relative to these, so all we did was just flip their order, right? And the 5, we took this 5 and we moved it over here, right? See that? But we also moved anyway, it's the same terms, they're just reordered. So this is called a rearrangement. And you do this, bit of common fractioning, and you get 1/2. And this, by the same mathematics that we haven't proved, this works out to log 2. So, yeah. So what I'm telling you is that if you just rearrange the terms in the alternating harmonic series, you can make it sum to a different value. That's messed up, isn't it? This is disturbing, is it not? So what's the moral of the story? Don't rearrange terms in a conditionally convergent series unless you want to change the outcome, right? Because it is simply not the case. This and that, they're not equal. Rearranging a conditionally convergent series can change the outcome. In fact, Riemann's rearrangement theorem, I can't spell Riemann. That feels wrong. It's got 2 R's.
I believe it's M-A-N-N.
M-A-N, okay.
Maybe.
Yeah. Well, I'm pretty sure that, well, anyway. Tell you what. Riemann's rearrangement theorem, there, problem solved. Riemann's rearrangement theorem says that if you have a conditionally convergent series, you can rearrange it to converge to any real number. You just play this game with moving stuff around. You can make this sum work out to whatever you like. Yeah.
So, would it make more sense if it was constant times natural log 2?
Well, the thing is, this works out to log 2. I will prove it eventually after the test. Seems to be a theme for today.
Oh,
but this, on the other hand, by this calculation, is 1/2 log 2.
Okay.
Yeah. Oh, again, the rearrangement doesn't, yeah, I can rearrange that, but they're not equal. Rearrangement is not allowed. It's not an allowed, rearrangement is not an allowed operation on series. It is forbidden. It's forbidden operation on conditionally convergent series. In fact, you can prove that for absolutely convergent series, an absolutely convergent series, any rearrangement won't alter to the sum. This is known. So the absolutely convergent series do not suffer this curious defect. So conditionally convergent is just kind of right on the edge of diverging in some sense. Because if you take the absolute value of them, they diverge. So they're not far from diverging in some sense, and so they behave strangely. Absolutely convergent series, on the other hand, they're absolutely convergent, so they behave nicely. Sorry, that's just an argument by words, but what else are you going to use? Let's see here. Sorry, I'm misbehaving. Let us move on. There are more examples, of course, and we will work more examples as you ask them. But I should tell you the ratio test and the root test, so we have completed our canon of tests. We have all of the tools. Ratio test says the following. Let the sum an be series with positive terms. Number one, the series sum an converges absolutely. When? When the limit as n goes to infinity of the absolute value of an plus 1 divided by an is less than 1. Okay? Number two, the series sum an diverges when the limit of that quotient is greater than 1. And it kind of bothers me in some sense that they even include 0.3 because it's worthless, but fine, I'll write it. 3, if, the limit as n goes to infinity of the absolute value of an plus 1 over an is equal to 1, then ratio test is inconclusive. In other words, it gives you nothing. For example, if you try to apply the ratio test to a p-series, any p-series, that limit works out to 1. Right, so then an plus 1 over an would be what? Yeah. Which so the ratio test is useless for analyzing the convergence or divergence of a p-series, which we don't really care about because we already know when they converge or diverge, right? So we wouldn't use the ratio test for a p-series because it's a p-series, we already know, But suppose we wanted to decide on the convergence or divergence of, I don't know. How about what example am I on? I lost track of it. 4 seems safe. So how about this one? The sum n equals 0 to infinity of 2 to the n over n factorial. Now, this guy is not geometric, right? You can take the ratio of successive terms. You don't get a constant. It's not that easy to compare to something, right? I don't even know what x to the factorial means, so like integral test is no help, right? I mean, how can you do this one? I don't think we can do that without like some serious thinking, given our current technology. But with the ratio test, this is a piece of cake. So we call this thing an, right? And notice that a n plus 1 over a n is equal to what? So to divide by an is the same as what? Multiply by the reciprocal, right? So this is really n factorial divided by 2 to the n. So I guess I should have made a point up here. Observe that an is greater than 0, right? Thus, consider okay. Can we simplify this? How does n factorial, what does n factorial mean, guys? Do you know? Maybe you don't know yet. Sidebar. Here's the way it works. 0 factorial is 1. 1 factorial is 1. But then n factorial is equal to n times n minus 1 factorial for n greater than or equal to 2. Yep.
The gamma function is actually in our homework.
Oh, well then I guess we do have more we can learn about. But yeah, short of fine. So I guess with the gamma function, integral test all of a sudden becomes possible, but still a difficult path. Yes. But anyway, so this is how factorial works. This is the definition of factorial. You know, you guys have seen factorial before? Some of you just seeing it for the first time. Anybody? Okay, for you, I will give you the first few values. I give you 0, I give you 1, 2 factorial, 2, 3 factorial, 6, 4 factorial, 24, 5 factorial, 120, 6 factorial, 720, 7 factorial, 5040. Okay, that's all I know. But this thing gets stupidly big, stupidly fast. I mean, it is bad. We just always multiply, you know, 4 times 3 times 2, 5 times 4 times 3 times 2. To get the next one, I would do 8 times 5040. Even by the time you get to 10 factorial, it's a really big number. It's hard to beat the factorial in terms of, if you see a factorial, there's only a few expressions which can kind of beat it. Do you guys know any? Like, what's bigger than the factorial? Exponential won't do it. Like, you pick anything you like, even a million. To the n eventually loses because n factorial starts getting more copies of numbers bigger than a million in its formula. It takes a while for n factorial to be bigger than a million to the n, but it'll happen. And once it happens, it keeps happening forever and ever. So no, that won't, I mean, any finite base exponential, but you kind of got the right idea. N to the n. That'll do it. See, because this guy is n times n minus 1 times n minus 2, 3 times 2 times 1, versus n times n times n times n times n full times. Right, so that inequality is clear. So yeah, n to the n will beat it.
What if you just did like 2n factorial?
Oh, so you're like n factorial is less than or equal to 2n factorial? Yes, you got me there. That's also good. But I was trying to get you guys to, well, anyway. This is very much a math major's answer to my question. I appreciate that. That's good. Anyway, so getting back to the problem, what we have here, what's 2 to the n plus 1 over 2 to the n? It's 2. So we have 2 times n factorial divided by n plus 1 times n factorial, right? Yes, sir. I'm trying to study the ratio of an plus 1 with an because I'm intending to apply the ratio test. To apply the ratio test, I need to show that the ratio limits to either something less than 1 or something greater than 1, which then either gives me convergence or divergence. So that's why I'm looking at the ratio. I'm going to use the ratio test, which is all about this thing. If I'm going to use the ratio test, I got to look at the ratio, yeah. If I'm going to do limit comparison test, I also look at the ratio, don't I? Right? But this is better than the limit comparison test because I don't have to pick another series to compare to, right? Anyway, you see what happens here is the n factorials cancel, right? Or reduce if you like, and we get 2 over n plus 1, which of course goes to what? Son of a motherless goat. Dang it. What? Well, that is most annoying. I thought this was... Oh, anyway, this goes to... I'm sorry, I'm an idiot. What does this go to? 0, right? As n goes to infinity? I'm sorry. I was just... See, talking about the limit comparison test poisoned my mind. Because the limit comparison test... it's got different... Anyway, so here, I just need that it's less than 1. Is 0 less than 1? Yep. So, thus, the sum, n equals 0 to infinity, of 2 to the n over n factorial converges, absolutely, in fact, by ratio test. Es bueno?
Where did the n factorial on the bottom come from?
Well, you see, n plus 1 factorial is equal to n plus 1 times n factorial. So that was, yeah. Good question. All right, Darius. In a battle of n to the n versus 2n factorial, who will win? What do you think? What's your intuition here? Converge, diverge? Yeah, I think it diverges. If you're brave, you could argue by the nth term test because n to the n over 2 to the n factorial, eventually it's obvious that that goes to something, it diverges to infinity as n goes to infinity. So this diverges by the nth term test, but I think it's probably healthy for me to like look at the ratio test here and see what it does. It'll give us some good algebraic practice if nothing else. So let's calculate the ratio here. Call this an, right? So clearly an is positive, right? So it's reasonable to try out the ratio test on this. It may not, like I said, I think nth term test, if you're bold, you can use nth term test here to argue divergence. an plus 1 over an. So that is, I'm going to emphasize, that's an plus 1 times the reciprocal of 1 over an. That informs what I write down here. So this is n plus 1 to the n plus 1 divided by twice n plus 1 factorial times, well, 2n parentheses factorial divided by n to the n. Now the question is, what on earth do you do with this thing, right? I think I'll write it over here. So how can we simplify this? I think I'm going to do is I'm going to peel off an n plus 1, right? If I peel off that n plus 1, then I have n plus 1 to the n divided by n to the n. That's harmless. And then I've got a 2n factorial divided by, now 2 times n plus 1 is what? This is 2n plus 2, right? So 2n plus 2 factorial is, it's 2n factorial times 2n plus 1 times 2n plus 2. Any questions? So this is really 2n plus 2 factorial, right? Which is 2n factorial times 2n plus 1 times 2n plus 2. The 2n factorial is still there. And I have n plus 1 to the n plus 1, which is n plus 1 times n plus 1 to the n. By laws of exponents, right?
Can you repeat that? Can you repeat that last part one more time?
This right here, I have traded for both of these terms. What? I have n plus 1 to the n plus 1 power. So that's n plus 1 to the n times n plus 1. Yeah. Now you notice what happens here, the 2n factorials cancel. And let's see here, what else do we got? We've got n plus 1 times, what is this? This is 1 plus 1 over n to the n power, right? And then we got 1 over 2n plus 1 times 2n plus 2. So what's going on here? I would point out, we can kind of rearrange things a bit. We've got the n plus 1 over 2n plus 1, right? We've got this 1 plus 1 over n to the n. And then we've got this lonesome 1 over 2n plus 2 over here. Each one of these converges to something in the limit as n goes to infinity. So this goes to what? The first term, leading coefficients, goes to a half. This one was one of our most handy-dandy. This is an example of 1 to infinity. I had an x instead of an n, but we worked it out. This limits to e. This one limits to, well, that one's easier. In fact, if you know the first two limit to something, it doesn't really matter what they do. This one kills it, right? This one sends it to 0. These three terms separately converge, so consequently the product converges to 0 as n goes to infinity.